Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Today we are going to explain safety analysis and optimization of a single pass shell tube heat exchanger using SolidWorks flow simulation. This is the model. Actually, you can see the model. Inside this one we have made a series of copper tubes, and these flanges are made up of brass, and these supporting bases we have made with iron, and we have made the shell with steel, and this inlet and this outlet valves made up of brass. We are having 4 valves, as you can see here. If you are to understand the flow passes inside this shell tube heat exchanger, let us cut this one from front end. I can see a better way. Okay, you can see. Actually, from this location, we will force hot water or hot fluid will be passing through this one, and as it is closed, so hot fluid will be passing through these copper tubes, and from here we will provide coolant, and you can see the copper tubes are closed at this location, so hot fluid will be passing through this exit valve, and here you can see one exit valve. This is the exit of the coolant. Okay, so let us start our simulation. Before starting, we should save it with a specific name. Let us save this one by the name of single pass shell tube heat exchanger. The leads have already been provided to make a complete closed geometry, and we have to start the simulation. And for starting the simulation, we have to create the flow simulation environment, and that can be started with the wizard itself. So we're starting from flow simulation, and environment is being created with wizard, keeping the name of the project as default project 1, and we're considering unit as SI system, and pressure will be Pascal, and temperature we'll consider as degrees centigrade as usual. Next, we're considering one internal analysis. It will be heat conduction in solids, and in this case gravity will be involved definitely, and you can check the direction of gravity. It will be y, you can see, so it will be minus 9.81 meter per second square along y direction, and along z direction it will be 0. Next, the fluid we are considering water only, so we'll be providing water at different temperatures. Hot water will be there, and by the same time cold water will be also there. Next, the material will be considering different materials. Let us select the default material as copper, and the other materials will be provided during application of boundary conditions. We're considering default outer wall thermal conditions and roughness, and atmospheric pressure will be 101,325 Pascal and 20 degrees centigrade temperature, and solid parameters will be again 20 degrees centigrade. Finish it. Now you can see the computational domain. We can hide this computational domain. We have to provide fluid subdomains because we are having 2 different temperature liquids, water at 100 degrees centigrade as the main fluid, and coolant will be working as water at 20 degrees centigrade. So we are providing fluid subdomains. And one thing, for providing fluid subdomains, it is suggested to have a segmented view of this model. In that case, we can provide fluid subdomains in a better way. Let us cut it along a front plane. Grain check. Now we can provide fluid subdomains. Insert fluid subdomain, and it will be water at 100 degrees centigrade as the hot fluid. It will be passing from this inlet location. You can see the domain. It is passing to these tubes only, and the remaining portion is vacant. That one is the space for coolant, right? This is the fluid subdomain for hot water at 100 degrees centigrade. Green check. Next, we have to provide subdomain, fluid subdomain for coolant. Insert fluid subdomain. It will be water at 20 degrees centigrade, and will be passing from this inlet location. Now you can see here, it is clearly visible that excluding these copper tubes, the remaining portion is for coolant. Okay, green check. Now material to be provided, we have to provide specific material. Solid material, insert solid material, predefined. It will be main metal will be copper for these tubes. You can select the tubes from the geometry itself. Selected, green check. Now we have to provide material for this shell. Solid material, insert solid material, and the shell will be made up of steels. We are taking stainless steel 3021 as the material for this shell. Let us select this separately. Green check. So material is provided. Next one, we have to apply boundary conditions, that means hot water and cold water from two different entries. Initially we are applying hot water at a rate of 1 kg per second from the hot inlet location, and temperature will be 100 degrees centigrade. That can be applied from thermodynamic parameters. 100 degrees centigrade. Hot water will be applied from this location. Green check. Done. Now again another boundary condition to be applied from this one, that means cold water at 20 degrees centigrade to be applied from here. So insert boundary condition, and the mass flow rate of cold water can be varied. It can be depending on requirement. In this case we are considering 0.5 kg per second for this cold water at 20 degrees centigrade. Let us see the thermodynamic parameters. It is 20 degrees centigrade and mass flow rate is 0.5 kg per second from this location. Green check. Two boundary conditions applied. Now we have to apply another two for these exit locations. Boundary conditions, insert boundary condition. It will be atmospheric pressure at the exit locations. Initial will take for this hot water exit location. Selected, green check. It is done. Now the last one, insert boundary condition. It will be atmospheric pressure at the exit of coolant, water at 20 degrees centigrade. So this location selected, green check. All the boundary conditions have been applied properly. Now we can have some specific goals. We can have a lot of goals. Let us select one global goal and some surface goals. Insert one global goal. That means we want to have average temperature of fluid inside this pipe as one global goal, and excluding that one we want to have some surface goal at the exit locations. That means pressure and temperature at the exit locations. Mainly we are bothered about temperature, so we'll see the temperature only. Pressure can be viewed from different cut plots also. So we have goals. Insert surface goals. We want to have average temperature of fluid at the exit of hot water. Selected, green check. And again another surface goal we want, that is the average temperature of fluid at the exit of cold water. Green check. Done. So three goals we have defined. We can rename this one as THO, that means temperature at hot exit location. We can denote this one THO. This is temperature at hot water exit. And second one, we can rename this one as temperature at cold water outlet. Next one, we have one equation goal, that is LMTD, it is very important to find out the effectiveness of these heat exchangers. So insert one equation goal, and this equation goal can be obtained from these input variables or these parameters. Let us select that boundary conditions to have the input parameters, that is temperature also, and mass flow rate, etc. will be required. The LMTD is equal to del T1 minus del T2 divided by ln del T1 by del T2. So del T1 is actually the temperature difference of hot inlet and cold outlet. Similarly, del T2 equal to temperature of hot outlet minus temperature of cold inlet. So we have to define it. So we can define del T1 as temperature of hot inlet, that is equal to 100 degrees centigrade. We can provide minus temperature cold outlet, that can be obtained from the goals. Whole will be within bracket. This is del T1 minus del T2. Del T2 is equal to the temperature difference of hot outlet and cold inlet. Hot outlet is obtained from the goal minus temperature of cold inlet, that is 20 degrees centigrade. We can provide from here. So this one also will be within bracket. Del T1 minus del T2. Now we can convert all these things within bracket again. Whole divided by ln del T1 by del T2. Let us copy this part. We can initiate another bracket here, divided by del T2. Copy, paste over here. You can see the equation. Let us provide green check to that one. This is our equation goal. We can rename this one as LMTD, logarithmic mean temperature difference. Right? You can see the complete view of the model, and let's run this one. We're starting new calculations. You can see the solver window has already started. It is preparing the model. Mesh refining is going on. Let the iterations move on. Whenever it is finished, we'll see the results and go for detailed analysis. We can see here right now the solver is finished. From the window itself, we can see that after 430 numbers of iterations, it has completed all these iterations, and from the results we can see that average temperature of fluid, it is 68.75 degrees centigrade, and temperature of cold water at the exitant is 40.9 degrees centigrade, and hot water temperature at the exitant is 89.74 degrees centigrade. Actually, for hot water we initiated from 100 degrees centigrade, and at the exitant it is reducing near about 10 degrees centigrade, and it is coming down to 89.74 degrees centigrade. Similarly, for cold water, its initial cold water temperature was 20 degrees centigrade, and it has gained a huge amount of temperature difference from 20 to 40 degrees centigrade. It is finally 40.9 degrees centigrade, and we got the value of LMTD as an equation goal as 64.275. Actually, more the LMTD, more is the heat transfer rate. Next one, we'll see the results from the cut plots, and also we see the dynamics of these hot water and cold water particles. Okay, so close this part. We'll see the results from cut plots. First, we see cut plots Like suppose when you see from right plane, and instead of pressure we'll see temperature of fluid. Green check. Now one thing, for visualizing these things, it is better to make this model transparent, then it will be clearly visible. Okay, so let's make the model transparent. We have changed the transparency of this shell, and for better viewing, let us make this wrap part hidden. Now you can see the flow pattern inside this shell. Initially at the entry point, temperature is very high, it is in the range of 100 degrees centigrade. As it is passing through the shell, its temperature is decreasing a little bit. And here at the entry of cold water also, you can see the temperature is very less. At the exit level, we can find that hot water temperature is in the range of 84 to 92 degrees centigrade. You can see. So at a different level, we can find different ranges, and some mixing is also there. That color range indicates temperature ranges at different locations. Okay. Now it will be better to see these things in the form of an animation. So what we'll do is, now before that we'll see that pressure difference also. Let us see pressure. You can see almost similar pressure is maintained inside this shell. Only at the entry and exit point of hot water it is different. You can see here also, right? Color is in the brown zone. That means its pressure is little bit reduced initially. You can see pressure distribution throughout this passage. Now what we'll do is, we'll see the distribution of temperature in the form of an animation. Okay, so temperature of fluid, we're going to see the cut plots of that in the form of animation. So let us see the cut plots again, and let's play it. You can see here, when water is flowing through these pipes or tubes, the temperature is in the range of red color. That means its temperature is very high inside these tubes, but in the cooling zone the temperature is increasing from 20 degrees centigrade to something else, right? Okay, now it is better to see from the front plane. Okay, so we'll cut this part and see from front plane. Let's clear and hide this part, and we'll see another cut plots from some different plane. Insert cut plot with respect to front plane. We'll see. Go and check. Now we can see these things easily. Let's see from front plane. Now color distribution shows the temperature throughout these pipes, and these vacant spaces are actually indicating coolant or cold water temperature difference. Okay, so we'll see these things in the form of an animation. Cut plot 2. Let's play this part. This is at the exit point. This temperature is red, and we can see here through these pipes temperature of hot water is changing. Even at the initial and exit point temperature is constant almost, but throughout these pipes, because of cooling, temperature is changing, right? You can see this way. Okay, done. So clear and hide this part. We want to see surface plots again. Surface plots, insert, and use all faces, and want to see temperature of fluid. Green check. Okay, it is very nice picture. You can see that entry and exit point temperature ranges are different. So and rotate in this way. This is the entry point. That means temperature of hot water is high range. It is in the range of 100 degrees centigrade, and as it is approaching towards the end of this shell, its temperature is changing, and in between we are having cooling zone. So there is a mixing of hot and cold water, so temperature is also varying accordingly. And again at the exit level, so cooling is not there, we are not having sufficient amount of cooling, so we are getting almost constant temperature of in the range of 84 to 92 degrees centigrade. And in between we can have some mixing. It is not actually direct mixing is not there, actually through convection what is getting mixed. This is the surface plot. Now next one we want to see the dynamics of these hot water and cold water particles. Let's clear and hide this part, and we want to see dynamics of flow particles. Okay, right? Flow trajectories. Insert flow trajectories. We want to see the dynamics of hot and cold both waters. Select other, select number 1. By the same time, we have to select the cold water also. Select other, and number 4. Both the lists have been selected. Now instead of 20 numbers, we can make it 200, and instead of pipes, we want to change it from pipes to arrows, and the size we want to decrease a little bit from 0.003 to 0.002, and we want to say temperature fluid. Go and check. It is done. Now you can see the mixing of water by the same time flow particles, how it is passing through the tubes, right? Better to see these things in the form of an animation. We'll see from front plane, from this plane itself. So we can see these things in the form of an animation. Flow trajectories, clear and hide, and let us play these things. We can see the dynamics. That means initially temperature of hot water is very high in the range of 100 degrees centigrade. It is approaching towards these copper tubes, and it is passing through the tubes, and from here we are forcing cold water for cooling purpose. And here in this case some kind of mixing is going on. Direct mixing is not there. It actually through convection, this hot water is reducing temperature, getting some reduction in temperature. By the same time, cold water is getting some gain in temperature, right? Let us clear and hide this part of flow trajectories. Clear and hide. Now let us see the goal plots. Insert. We decided some specific goals. We want to see all of them. First one was average temperature of fluid, then exit temperature of hot water and cold water, by the same time LMTD as an equation goal. Let us see these goals. Now we can see that average temperature of fluid is 68.76 degrees centigrade. Its minimum was 68.66 and maximum was 68.76. And hot water at the exit location is 89.75 degrees centigrade. So it has lost huge amount of heat. Its initial temperature was 100 degrees centigrade, and at the exit level its temperature is reduced to 89.75 degrees centigrade, and average value is 89.87 degrees centigrade. Similarly, cold water, its initial temperature was 20 degrees centigrade, and at the exit level it has gained a huge amount of heat, and its final temperature is 40.9 degrees centigrade, and average temperature is 40.58 degrees centigrade. Similarly, LMTD, it is dependent on both the ends, hot and cold, and it is depending on exit and entry both levels. And finally we got the LMTD of this heat exchanger is 64.28, right, and average value is 64.5. Now more the LMTD, more heat is transferred. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.